I welcome you all to the session of engine system and performance, and today we shall discuss about this part, that is electronic devices which are used in ECU, and then we shall be discussing this particular part taking an control system layout, and thereafter we shall discuss about two different types of sensors in today's class. So, what we learned from our previous classes is that electronic control unit, which is also known as engine management system, is very important for the modern engine, because this system is responsible for the safety and smooth operation of engine, to meet the emission guidelines, and also to allow for the engines to be operated always at its design condition. So, now what we have learned is that electronic control unit is receiving some inputs from different parts of the engine, and then depending on the requirement, this part sets on some correction to be done, and then accordingly we get some output from the ECU, and those output are necessary to adjust engine with the changed or altered conditions. So, you know that before going to this layout of control system, let us first discuss about some introduction about the sensors, why sensors are needed, what should be the input to the sensors, and then what type of output we are getting from the sensor. We all know that sensors are essentially provided to pass on some information about the operating state of an engine. As I said you that if a particular engine is not operating or is not running with the designed condition or design value, certainly that information should be reached to the electronic control unit or engine management system, and then electronic control unit or engine management system will do some corrections, and those corrections should be conveyed to the sensors which will be there in another or different parts of the engines. So, as I said you that sensors are provided to pass on some information about the engine operating state or about the operating state of engine. So, if I write down here, at least it is important, sensors are provided to pass on some information about the operating state of an engine. Now, question is, if sensors are really needed to do this, I mean if the task of a sensor is to provide some information about the current operating state of engine to the electronic control unit, engine to the ECU or engine management system. So, this is basically the objective of a sensor. Now, if sensors are needed to provide some information to the ECU about the current operating state of an engine, certainly there must be some input to the sensor and there must be some output from the sensors. So, now what should be the input to the sensor? Before going to discuss that particular part, question is, sensor will receive about the current operating state of an engine, then can sensor really provide those information directly to the electronic control unit? No. So, basically sensor in a control unit or in a control system, sensors are provided to measure the physical variables, rather the operating state of an engine, and they will provide some measurement, some information in the form suitable for the microcontroller. So, that means sensors will receive some information and it is not a case that those information will be directly conveyed to the electronic control unit. So, in a control system or in a control unit, sensors are provided to measure some physical variables. Those are important to dictate the physical or operating condition of an engine, and those physical variables will be measured in the form suitable for the microcontroller. So, that is which is very important. So, if I write here that sensors measure physical quantities, these physical quantities are responsible to determine or dictate the operating condition of an engine, right. So, sensors measure physical quantities in the form suitable for microcontroller, right. So, this is important. Now, question is then what should be the input to the sensor? Typically, input to the sensor is any physical variable of the plant being controlled. So, if I write over here, so let us now write input to the sensors. So, any physical variable of the plant being controlled. So, this is the input to the sensor. Then what should be the output from the sensor? So, output from the sensor. This is always an electrical signal. This is always an electrical signal. Now, this is what we know by this time. So, input to the sensor should be any physical quantities, that is how the sole function of a sensor should be. So, receiving any physical quantity or any physical variable, those physical variables or physical quantities are responsible to dictate the current operating state of engine, and then output should be always an electrical signal. Now, question is, if we talk about ideal sensors, typically ideal sensors respond to any particular physical quantity, but in reality no sensor can be an ideal sensor, because output, as I said you that ideal sensors respond to any physical quantities or stimulus, but ideal sensors are not there. In real applications we call them real sensors, and real sensor respond to physical quantities or external on stimulus in some way, and let us now discuss what is in some way to that physical quantity or stimulus. So, ideally input or ideally sensor responds to only one physical quantity, but in real case sensors respond in some way to that physical quantity or stimulus. Say for example, if we have a sensor and if the sensor is measuring pressure, say for example, if we have a sensor and that sensor is integrated to the intake manifold, and sensor is responsible to measure the pressure of air or incoming air, because we know without a pressure difference there cannot be any flow. So, at the inlet of intake manifold, if we have a sensor, if the sensor measure the pressure of the air, and now question is that pressure will change if the surrounding temperature or temperature of the ambience changes. So, whenever sensor will respond to that change in pressure, or if we consider that is stimulus, certainly we have to take into account the change in pressure due to change in temperature. So, in real application sensors respond in some way to that physical quantity. Certainly, if through proper signal processing we can eliminate that defect. Okay. So, now let us, we have discussed about one thing, that is ideal sensor responds to only a physical quantity or stimulus. Right, but in reality we have real sensors responds in some way to the physical quantity being measured, to physical quantity being measured, and we have explained about this. So, at least you have understood the difference between ideal and actual or real sensor, but in reality no sensor can be an ideal sensor. Okay. So, now let us discuss about the control system, rather this is a typical layout of the control system for the SI engine. So, I should write here that this is engine management system for SI engine. So, this is for the spark ignition engine. What we can see, as I said you, that to ensure safety of the engine, to ensure that the engine should run always at its design condition, maintaining the let down guidelines of the emission level, we should have this particular system, that is engine management system or electronic control unit, and this system is reliant on a few sensors, and those sensors are responsible to provide some information about the engine operating state to this ECU or engine management system. So, altogether all these things are known as engine management system, that is what we have discussed in one of the previous classes. So, what we can see from this particular diagram, that we have engine speed sensor. So, this sensor will receive some information about the speed of the engine, and receiving that information sensor will provide some output. As I said you, output is always an electrical signal, and that will directly go to the microprocessor system. Try to remember, we said that sensors measure physical quantity, say for example, if it is the speed of the engine in the form suitable for the microcontroller, and that information will go to this microprocessor system, and eventually from there some information will go to the engine so as to control, engine that is plant or that is ECU or engine management system, so as to control something. Maybe we need to increase the combustion rate, we need to supply more amount of fuel, all these things. Now, there is another important sensor, that is crankshaft position sensor. So, if we now mark here, this is crankshaft position sensor. We have another one, that is spark timing feedback sensor. We have engine temperature sensor, we have throttle position sensor, we have mass airflow sensor. So, all these sensors are needed. This engine speed sensor is responsible to measure the speed of the engine. Crankshaft position sensor is very important for the fuel injection and ignition system control. So, to know about the total time of fuel injection, to know about the ignition delay or ignition lag of the engine. Spark timing feedback sensor is also very important in the context of spark ignition engine, because that sensor is responsible to give some information about the spark retardation or spark advancement. to meet the demand. Engine temperature sensor, you know very well that, which is again a very important sensor for the modern engine, that we need to know about the engine operating condition, engine temperature. So, sensors can be integrated to the cooling water jacket. That sensor also can be attached to the intake manifold to measure the temperature of incoming air. So, incoming air, the air which should be, the air to be drawn into the engine cylinder should have some specified temperature and pressure, so as to ensure the combustion would be efficient. Then we have throttle position sensor is also very important to control the load. As I told you that if the, say for example, engine is running at a 45 km per hour. Now, if engine or if the vehicle which is having a which is having an engine, and if the engine is running at, or vehicle is running at 45 km hour, so engine is generating some certain amount of load, power. Now, if the vehicle needs to uphill, certainly driver need to adjust. So, if we do not have the provision of knowing that engine is uphilling, that information should not reach to this electronic control unit or engine management system, and then engine speed will reduce. So, the vehicle speed will reduce. So, this throttle position sensor is responsible to adjust the air fuel mixture, that is the amount of charge to be supplied to the engine cylinder, if it is a SI engine. If it is a CI engine, again certain mass of air to be drawn into the engine cylinder should be controlled by this particular sensor. Again there is a sensor which is mass airflow sensor. So, all these sensors are very much important to run the engine, whether the engine is a locomotive engine, whether the engine is a stationary engine. For both the cases, these sensors play a very important role for a safety and smooth operation of the engine. And as I told you, receiving some input from all these, sensors will receive input from the plant being controlled. Plant is engine here. Receiving some input from this sensor, that is microprocessor, microcontroller or microprocessor system, will give some information to the ECU or engine management system to set up some corrections, so as to spark timing can be controlled, air fuel mixtures to be supplied to the engine can be controlled, rather mass of air fuel mixture, and also the fuel injection time period can be controlled. So, we have understood about all these, and this is how an engine management system or an electronic control unit works. And as I told you that if we look at the schematic depiction, we can see there are two important type of sensors. In fact, all sensors are very important for the safety operation of the engine, but in today's class we shall be discussing about two important sensors. What are those? So, if we try to mark them, one sensor is engine temperature sensor and another one is, so we shall be discussing about temperature sensor. I should write here air or coolant, because measuring the temperature of incoming air we can control the combustion rate. Measuring the temperature of the coolant we can have some information about the engine present condition, right. So, air and coolant temperature sensor, that we will be discussing today, that is number one, and then also we will be discussing this crank position sensor, number 2, that is crankshaft position sensors. So, now let us quickly discuss about the first one. If we go here, again you can see this is the schematic depiction. So, I have tried to have the schematic representation of this particular sensor, so as to make you understand this sensor functionality and also hardware. So, what we can see that this sensor, which is air stroke coolant temperature sensor, because as I told you that the same sensor can be used to measure the temperature of incoming air temperature or temperature of incoming air. The same sensor can be used to measure the cooling water temperature, so as to know indirectly the temperature of the engine block or engine cylinder. This sensor, let us first discuss about the hardware, then we shall discuss about the operating or operational procedure. So, what we know before going to discuss about the hardware and also the operational procedure of this particular sensor, let us first discuss why do we need to have a sensor to measure the temperature of incoming air. As such, if you try to recall, in one of the previous classes we have discussed that measuring the temperature of incoming air is very important for the efficient or smooth operation of the engine and efficient combustion. So, let us revisit that once again. We know that mass of air to be drawn into the engine cylinder. So, that is m dot air. So, if we write here, we can write this is rho I V s and then eta volumetric. So, this fellow, if I just write over here, this quantity we have used here, this is volumetric efficiency. Why we have multiplied this quantity with eta v, that is volumetric efficiency, because you know if we just consider these two terms, certainly we will be getting a theoretical amount of mass of air to be drawn into the engine cylinder, but in real case it is not this situation or scenario. So, actual amount of or actual mass of air should be taken into the engine cylinder for a given throttle position and for a given cycle should be always less than theoretically calculated value, and that is why this volumetric efficiency is there. And you have studied this part in your undergraduate internal combustion engine course. Now, Vs is, this is swept volume, and most importantly the quantity which will govern the amount of mass to be drawn, mass of air to be drawn into the engine cylinder is this, that is density of incoming air. So, what we can do, we can have this expression in a bit different form, that is we can write Pi by RTI Vs eta V, whereas the subscript I stands for the incoming quantities. So, Pi by RTI. Now, you can understand that if we can have air with low temperature, then it would be more denser. So, that means somehow if we can control the temperature of the air or incoming air at a level for which for a given throttle position or throttle opening and also at a given cycle, greater mass of air can be drawn into the engine cylinder. If we can have larger or greater mass of air in the engine cylinder, then certainly the combustion rate will increase and we can have we can produce more power output. So, but if temperature increases, that should be that is very likely, because depending on the ambient temperature of the air which is taken into the engine cylinder will vary. If temperature increases, then certainly we can understand the mass of air to be drawn into the engine cylinder even for a given throttle position and for a given cycle should be reduced. And if this is the case, then again combustion rate would be reduced. Not only that, in absence of adequate amount of mass of air, fuel supply should remain fixed, then we will not be able to control the guidelines or let down guidelines of the emission level. So, what this sensor does, the sensor can be attached to the intake manifold, as I told you, to measure the temperature of the incoming air, and also the sensor can be attached to the cooling water jacket to measure the temperature of the engine block or engine cylinder. So, now let us come to this particular part. We can discuss this little bit of hardware of this sensor. What we can see, the sensor is having a hollow sealed brass tube. So, you can see that a brass casing. So, both ends are sealed. So, this sensor containing a hollow sealed at both ends brass tube. Inside the tube we have a semiconductor resistance, this negative, I mean I will be discussing though. So, this inside this tube we have a semiconductor resistor having a negative temperature coefficient, and from the sensor you can see the electrical connection part is there. So, will be, as I told you, output from any sensor, from the sensor is an electrical signal. So, certainly this electrical connection is there to get that signal. Now, this is also known as thermistor. Let me write here, thermistor air temperature sensor. Now, let us discuss about the operational procedure of this particular type of sensor. As I told you that this sensor is having a semiconductor resistance having negative temperature coefficient. So, we need to look at again the figure that is there in the inset of this schematic depiction, and if we focus our attention on this particular curve, that is negative temperature coefficient. What does it mean? With increasing temperature resistance drops, right. So, this particular semiconductor resistance is incorporated to this sensor, and when there is a change in ambient temperature, ambient air temperature, this sensor is responsible to measure the temperature, provide some provide some output signal. That signal is given to the microcontroller, and that microcontroller even gives some information to the control unit to set up some correction so as to control the mass of fuel to be injected into the engine cylinder, and the mass of fuel should be injected into the engine cylinder in such a way that it should be stoichiometric air fuel mixture. So, now let us discuss. So, this semiconductor resistance is having negative temperature coefficient, with increasing temperature resistance drops. If I write here, you know that this semiconductor resistor has a negative temperature coefficient, that you can see from this inset figure. With increasing temperature resistance drops. I can give you some information about this sensor, that at minus 40 degrees Celsius resistance is 1 lakh ohm. Now, if we increase the temperature, say for example, air temperature of the ambient air is increasing, and that will certainly affect the mass of air to be drawn into the engine cylinder. So, this semiconductor resistor can work in the range when temperature is even 130 degrees Celsius, then resistance drops and becomes 70,000 ohms. So, you can see that this is the range of the temperature for which this thermistor air temperature sensor can work. Now, if temperature increases, then resistance will drop. If resistance drops, then there will be some voltage alteration. That information will be given by the sensor to the microcontroller, and that microcontroller will give some feedback to the electronic control unit, and what electronic control unit will do, receiving that some mismatch in the voltage output from the sensor, because certainly the voltage at a higher temperature of the incoming air should not be the designed or accepted voltage from this particular sensor. So, a change in voltage from this sensor will be read by the microcontroller unit, and that microcontroller unit will give some feedback to the electronic control unit, and then electronic control unit will set up some correction so as to control the fuel injection time. So, now let us discuss about why do we need to have fuel injection time control. So, if temperature increases from say for example 20 degrees Celsius to 50 degrees Celsius. So, a reduction in resistance of the semiconductor resistor will alter the voltage, and that voltage will be that output signal will be taken by the microcontroller. Microcontroller will give some input to the ECU, and ECU will try to adjust the or set up some corrections so as to control the fuel injection time. So, with increasing temperature, mass of air to be drawn into the engine cylinder for a given throttle position or throttle opening will reduce. So, if we do not give some input or give some information to the fuel injection valve that please try to reduce the fuel to be spread into the engine cylinder, then excess fuel in absence of inadequate air will create some additional issues like combustion will not be proper and emission level will increase. So, that means receiving that signal, ECU will give some information to the fuel injection valve to reduce the fuel injection. So, to match the air and fuel ratio, and it should be stoichiometric air fuel ratio. So, this is how this air temperature air or coolant temperature sensor works. So, now let us discuss about another important type of sensor. As such, I should say this crankshaft position sensor is the very important sensor for the modern engine, and this sensor is used to control the fuel injection time and also the ignition system. So, if I write here that this sensor crankshaft position sensor is a very important sensor for the fuel injection system and ignition system of the modern engines. So, for the modern engines, if we need to control the fuel injection time, if we need to control the ignition timing, this particular sensor plays a very important role. So, now again let us look into the schematic depiction. What we can see from the schematic depiction, there are two different types. One is variable reluctance sensor, which is also known as magnetic pulse generator type sensors. And in the bottom panel of the schematic, we can see Hall effect sensor, which is type B. So, this is type B. Now, this variable reluctance sensor, which is also known as magnetic pulse generator type sensor, is also known as two-wired sensor, because this is having two different wire. So, this is also known as two-wired sensor, whereas this particular type Hall effect sensor is also known as three-wired sensor. Now, question is, you can see the extreme left part where there is a toothed disc. So, this toothed disc, basically this is a shaft. So, now question is, that we need to know the shaft position. So, basically shaft speed, right. So, crankshaft. So, this sensor can be located either on the crankshaft or on the distributor shaft, and this is you can see this is a toothed disc. So, if I write, so this is toothed disc, and this sensor is this sensor works following non-contacting method typically electrical or optical. So, you can see there is no direct contact. So, the toothed disc, as I told you, the sensor can be placed or located either on the crankshaft or on the distributed shaft. So, now this is non-contact type because there is no direct contact between this toothed disc and the sensor. And what you can see for the first one, that is magnetic pulse generator type or variable reactance sensor, there are two different wires. I mean these two wires, it is because of this presence of two wires, it is also known as two wire sensor. And the output from this sensor is an analog signal. So, if I write here that output from the variable reluctance sensor is an analog signal, right, whereas for the Hall effect sensor output is a digital signal. So, if I write here output from the Hall effect sensor is digital signal. Now, question is, we can see 3 wires in this particular type sensor, and this particular sensor, for this particular sensor, that is Hall effect sensor, we need an external voltage supply or external voltage source, unlike the 2-wire sensor. For the 2-wire sensor, there is no need of having this external voltage source, but for the Hall effect sensor we need this. As I said you, this sensor works following purely non-contacting method. Typically these sensors employ electrical or optical method to get some excitation, and this toothed disc is one which excites sensor producing a signal, and that signal is basically analog signal for the variable reluctance sensor output certainly, and it is digital signal for the 3-wire sensor, and that signal is again passed to the electronic control unit so as to control or so as to set up some correction therein, and some information will be given to the fuel injection valve so as to reduce the fuel injection time, and that information can be even passed to the ignition system so as to control the ignition time. So, to summarize our today's discussion, we have discussed about the sensors. To be precise, some introduction about the sensors. We have discussed about the input and output of a sensor, what type of input of a sensor will receive, what should be the output from the sensor. Then we have discussed about a typical layout of the control system essentially for the SI engines, and then we have discussed about the operational or operational principle of 2 different sensors. One is the air coolant temperature sensor and the second one is crankshaft position sensor. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.